We've been using the van der Waals B constant as a volume, and I wanted to talk a little bit about why that is, and what is the van der Waals B constant, what is the van der Waals equation, and why are we using it as a volume. Hopefully this looks familiar. This is a pressure temperature graph for water that we call a phase diagram in Chemistry 400, and the phase diagram includes from 0 atmospheres to 218 on a non-linear scale for this one. In fact, this is from my Chem 400 class, and temperature all the way out to 647, low of 0 Kelvin, all in Kelvin and atmospheres here. And what we've talked about before, at least in Chem 400, my Chem 400 class, is there's a solid phase, there's a liquid phase, and a gas phase. And out here is what's called the critical point, and we're going to see that again. That's point E here, and point D is the triple point. The triple point is where both the solid, the liquid, or sorry, not both, all three of the solid, liquid, and gas phases can coexist at this one specific pressure and temperature that's marked right here. The critical point is the above which you can go from liquid to gas without having any phase transition. Now that last plot was pressure versus temperature, and this is pressure versus volume at a constant temperature, and this is what is related to Boyle's law in Chemistry 400. And Boyle's law says P1V1 equals P2V2. That it means that pressure and volume are inversely related, meaning that as you go to lower volumes, you get higher pressures, and as you go to higher volumes, you get lower pressures. And so again, this is something we've seen. We may or may not talk specifically about whether or not the fact that temperature is constant on this line, but it's true. And we're going to do lots of these pressure volume plots coming up. Now let's look at some real data. This is, again, pressure versus volume. This is a graph, and now we've got multiple temperatures on here. This is real data for carbon dioxide. And we do have different units for pressure, and now we're using something called specific volume, which is the volume per kilogram instead of moles. It's the meter cubed, which is volume per kilogram. So kind of weird units, but we'll deal with it because it shows what we want. What it shows is the critical point and what it looks like on a pressure volume picture. And the critical point here for carbon dioxide is 304.1282 Kelvin, pretty specific. And you can see at temperatures higher than that, the curves sort of bend a little bit. And these are going, this is like a close-up near lower pressures and low volumes, as you can see. But they're going to gently curve, so they're going to, let's see, curve, well, I don't know if you can see that, but they're curving. They're still that same shape as we showed in previous plots. But then as you get to the critical point, you get this little flat part. And that's how you actually identify the critical point. It is the one point at which the slope of the pressure versus volume at a specific temperature has zero slope, and in fact there's also a change in the curvature. And for those of you who have had calculus, you know that zero slope is going to be the derivative is 0, and that changes in curvature are going to mean that the second derivative is 0. And we are starting to see why calculus is an important thing as we do research, so that we can understand what others have done and hopefully even what we're doing. Okay, now let's get below the critical point, say at 300 Kelvin, right? Critical temperature is 304 something Kelvin. And what we're going to see using the van der Waals equation of real gases, another Chem 400 touchstone that at least we talk about in my class, you start to see that, where's your cursor? That you get this bend in it. So you get just sort of at high pressure, low volume, it gets high, and then it goes down low down here. But in the middle, there's a wiggle, and the wiggle as it goes from so lower and then higher here, this is going to be the liquid gas coexistence region defined by this area here. And over here is going to be the volume at a specific pressure and temperature of the liquid. Go straight across, and that's the volume of the gas. Of course, the gas has a lot more volume, a lot bigger volume. Go down to 290, and you'll still see the same thing. They're not showing the van der Waals isotherm, but it would go down, come up, and connect over there as well. And so when this, let's say this is real data, and then modeling it using the van der Waals equation of state, the van der Waals equation for real gases, both of those names are names that we're going to use for, as we'll see. Now, the van der Waals equation of state. So review, so here's the equation down here. It takes into account, so it's a real gas equation. It takes into account that there are attractions between the particles. Those attractions lead to a lower pressure. So this term right here adds some pressure back in to make make the behavior back to that of an ideal gas law equation. That a real gas has takes up less volume, so we have to subtract some volume off here in order to make it a real gas. And so if we take this term here, minus NB off, and we take the plus AN squared over V squared off, we get back the ideal gas law. And we see we have A and B, which are two constants, whereas N is the number of moles. We have pressure, volume, number of moles, and RT in this equation. And you can see our B term here. Good news. Hopefully we're one step closer to understanding it. All right, now we're talking about the van der Waals equation of state, which is shown right here. What we want to say is that this is a cubic equation in volume, and we can show that because as we multiply this out algebraically, we'll get PV squared, so that we have a common denominator for this term. So we have V squared up top, and then we multiply it times this V term. We end up with a V cubed term. Multiplying this out a little bit more and then getting the V cubed term by itself by dividing by pressure, we can end up with an equation like this, which has a V cubed term, V squared, V, and just a number. In terms of the other variables, pressure, A, B, are van der Waals constants, as we'll see, and N, number of moles, R, the universal gas constant, temperature as well. And this van der Waals equation of state, that's our new name for it. And there are many equations of state, actually, but this is one of them. Can also be solved for P, where I cut this out of a document, copied and pasted, that had P as a lowercase p, but it's still pressure. We can solve this for P as well, because what we're going to do is we're going to plug in volumes, temperatures, A and B values for gases, and moles, although I think we'll use molar volume, so these moles terms will cancel out. Molar volume just means that the volume will be 1, and this V should be V sub m for molar volume, volume per 1 mole. Anyway, details. So let's plug that in. And what we get is a graph just like this. We've seen something similar before, except now we've got the critical point again is this red line, which is K. And what we said before is that if we want to find this critical point, that we have to take each of these lines at constant t. We're going to solve for the slope of the PV line. These are pressure volume lines. I can, I got my big head in the way here, at least while I'm recording this. Maybe I'll move it up here. But when the slope of the PV line is 0, right, slope of 0, and the curvature changes from a positive curvature to a negative curvature, and those just mean the slope is 0 and the first derivative, which is the slope, is 0, and the second derivative is also 0. And you can see these are, not to worry you too much, partial derivatives because we are keeping temperature constant, and a partial derivative is the same as a regular derivative when you keep something else constant. Anyway, at T greater than the critical point temperature, those are the light blue lines up here, there is no point at which this is true. So there's no point at which the slope and the curvature change. At T less than the critical point temperature, since the van der Waals equation of state has a cubic behavior, you get up to 1, 2, 3 kind of roots. I know they're not technically roots because they're not on the 0 line, but there are 3. That's basically the structure of this. You get this shape like this. And then at lower temperature, you get the shape, and you can even get negative values of pressure, which are not physical, right? In fact, this whole region isn't physical. What we said from the last graph is as you go from here to here, and I have to think about why it's right there, but because these areas are the same, I think. Something to do with that. Anyway, that's the liquid volume at this temperature, and this is the gas volume at that temperature. And since we went on, let's just continue. I accidentally clicked. What is B? Well, we can now have the van der Waals equation, solve it for P, and then differentiate once with respect pressure with respect to volume. That's what this looks like, which means while temperature is constant, so temperature will be a constant, meaning it will not affect the derivative part. It'll just go through, it won't have its own derivative issues, let's say that. Anyway, if you've been through first semester calculus, you should be able to understand that the derivative of this equation is right here, which we can set it to 0. And then we can differentiate it again and get the derivative here and set it equal to 0. And then what we have, delightfully, is A and B as our 2 unknowns and 2 equations for them, so we can solve for them in terms of the other constants or variables. Parameters, I think, is the right term. All right, now as I said, we have 2 equations and 2 unknowns. Let's solve these. For the algebra, there's a link here, but what we end up with is something called the critical temperature, which is the temperature at the critical point, critical pressure at the critical point. We're putting those C's there just to indicate that we're solving them for the specific conditions that we've already taken into account, that the slope and for the first derivative and the second derivative, the slope and the change in curvature are both 0. And we get this, and in particular, we're worried about the critical temperature and the critical pressure because these two will have they'll have A and B, and we'll have 2 equations, so we can actually solve these for A and B. Interestingly, you can do the reverse and get an idea of what the critical temperature and pressure are potentially as well, and the critical volume too. Let's see. Good, all those steps are in that file. And now what I'm going to do is I'm going to take these 2 and show a little bit of the algebra So I can take this pressure critical equation and solve it for A, plug it into the TC equation, cancel some things out, and I get an expression for B. B is the van der Waals B, and we can calculate it for any material upon which we have the critical temperature and pressure. And the critical temperature and pressure are widely cataloged. Just like in Chem 400, we have widely cataloged the delta HF values, and in Chem 401, we add the delta H, so delta G formation and S values, my favorite, entropy. No delta S for this, at least for the tables. But so the temperature, critical temperatures and critical pressures are widely cataloged, and now we can estimate for anything, any gas, the B, and B will have units of milliliters per mole. You can change the units, but that's typically what we're using right now. We may have to change units coming up, but so far that's what we're using. And so far what we're doing is we're treating that as a volume, and we're ratioing the volumes. So a lot of what we do is independent of what the units are. Okay, what is B? B is literally the molar volume of the gas phase molecules that, when subtracted right here, makes the volume portion of the ideal gas law correct. It is also called the co-volume. It is generally considered to be related to the excluded volume, although the little bit of work that I've been doing says that this is much more well understood, or there's been a lot of work on gases, like atomic gases like helium, but it is associated with the excluded volume. It has been associated with what's something called the polarizability volume and the packing fraction. And we're not talking about what that means for the packing fraction today, but believe me, I'm looking into it because we are packing molecules in our binary solutions.